Today we are doing section 1.4, the matrix equation AX equals B. Linear combinations can be viewed as matrix vector multiplication. Definition: if A is an m by n matrix with columns A1, A2 all the way to AN, and vector X is an Rn, then the product of A and vector X, denoted A times X, is the linear combination of the columns of A using corresponding entries of X as weights. And there is just one A missing right here. So make sure when you have this should be A times X equals, here you have your columns of A, your weights of X, and then it would be A1 times X1, A2 times X2. Example 1. Find the matrix equation AX equals B if A is 1, 3, 0, negative 4, 2, 5, and X is 7, negative 6. So this would be our first matrix, 1, 3, 0, negative 4, 2, 5, times 7, negative 6. This would be 7 times 1, 3, 0, so column times row, plus negative 6 times negative 4, 2, 5, giving us 7, 21, 0, plus 24, negative 12, negative 30. So our answer, we would just add those together. You should get 31, 9, negative 30. And that would be your answer. Let's look at example 2. Write down the system of equations corresponding to the augmented matrix below, and then express the system of equations in vector form. And finally, the form AX equals B, where B is a 3 by 1 matrix, or vector. Okay, so our corresponding system would be 2x1 plus 3x2 plus 4x3 equals 9, minus 3x1 plus x2 equals negative 2. So this is your corresponding system of equations. Next, we want to write our vector equation. So it would be x1 times 2, negative 3, plus x2 times 3, 1, plus x3 times 4, 0, equals 9, negative 2. And this is your vector equation. And then finally, our form of AX equals B would be 2, 3, 4, negative 3, 1, 0, times x1, x2, x3 equals 9, negative 2. And you need to know all three of these forms. Because you will be asked to go from this matrix to a corresponding system, to a vector equation, to a matrix equation in a problem. Three equivalent ways of viewing a linear system. 1, a system of linear equations. 2, a vector equation. And 3, a matrix equation. So those are the three ways that we did in the previous example. Theorem 3. If A is a m by n matrix with columns A1 all the way to AN and B is an Rn, then the matrix equation AX equals B has the same solution set as the vector equation x1 times a1 plus x2 times a2 plus all the way to xn times an equals b, which in turn has the same solution set as the system of linear equations whose augmented matrix is a1, a2, an, b. And a useful fact is a linear equation ax equals b has a solution if and only if b is a linear combination of the columns of A. Example 3. Let A, so that would actually be A, it's formatted a little differently, equal 1, negative 3, 2, 4, negative 11, 8, 5, negative 14, 10, and B, B1, B2, B3 is the equation AX equals B consistent for all B. So this is our augmented matrix corresponding to AX equals B. So the first thing is we have our augmented matrix corresponding to AX equals B. And what we're going to do is we're going to row reduce to see if we have something that would make this consistent. Okay, so what we can do is take a minute and try to row reduce this to get something consistent. And the first thing I'm going to do is take negative 2b1 and add it to b3. So negative, 2 row 1 and add it to row 3. So row 1, I'm going to leave the same. And then the next thing I'm going to do is I'm going to take 3b1 or 3 row 1 and add it to b2. And I can stop there. This isn't consistent for all B since some choices of B make negative 2b1 plus b3 non-zero. So here we have a definition. The columns of A span Rm if every vector B in Rm is a linear combination of A1 to AP. Theorem 4. Let A be an m by n matrix. Then the following statements are logically equivalent. For each B in Rm, the equation AX equals B has a solution. For each B in Rm is a linear combination of the columns of A. The columns of A span Rm. A has a pivot position in every row. So let's look at this example. Okay, so the formatting is a little different than previous years. So let A be 1, 3, 5, 2, 4, 6, and B be B1, B2, B3. Is the equation X equals B consistent for all B? So our augmented matrix would be 1, 3, 5, 2, 4, 6, B1, B2, B3. I'm going to go through and do the work. Some of you are probably already looking at it and being like, and know the answer. So this could become 1, 2, B1, and I could take B2, row 2 minus 3 row 1 and get 0, negative 2, B2 minus 3B1. And with the last one, I could take row 3 minus 5 times row 1 and get 0, negative 4, B3 minus 5B1. And from here, I then, in the bottom row, could take and subtract 2 times the second row and zero it out. So I would have 1, 2B1, 0, negative 2, B2 minus 3B1, and 0, 0. B3 minus 5B1 minus 2 times B2 minus 3B1. And right there, you don't have 0 equals 0, so it's not consistent. And also, it wasn't a linear combination from the very beginning. Example 5. Do the columns of A span R3? So we're missing span R3. So right in here, we should have span. Okay. So we would have 1, 2, 0, 2, 4, 3, 3, 6, 9. I can reduce this and get 1, 2, 3, 0, 0, 0 by negative 2 times row 1 plus row 2 and 0, 3, 9. Okay, the columns of A do not span R3 because there exists a row in the form 0, 0B. Because here, I would end up getting, if I multiply this, I'd have 0, 0B. So right from there, the columns of A do not span R3 because there exists a row in the form 0, 0B. Therefore not consistent. And you may have done it a little differently or have a different reasoning from a different definition. And then our last theorem, if A is an m by n matrix, vector u and vector v are vectors in Rn, and C is a scalar, then A times vector u plus vector v is just A times vector u plus A times vector v, and A times the scalar C times vector u is C times A vector u.